looking at homework 6s for both of these. All right, so number 8 on homework 6 was this division of complex numbers problem. So when we have a fully complex number in the denominator, so something that's got a real part and an imaginary part like this one, where the 3 is the real part and the 2i is the imaginary part, the trick is we're going to multiply the top and bottom by the conjugate of that denominator. So the conjugate is the same thing with just a different sign in the middle. So instead of 3 minus 2i, I'm going to do 3 plus 2i. And then I'm just going to FOIL things out. So I get 12 plus 8i plus 21i plus 14i squared. And the bottom I get 9 plus 6i minus 6i minus 4i squared. So if I combine my like terms, the 6i and negative 6i cancel out, and 8i and 21i become 29i. And then I remember that I squared is the same as negative 1. So I have 12 and then minus 14, so that's negative 2 plus 29i. And down here I have 9 minus a negative 4, so that's going to be 13. And then I would just rewrite these then as 2 fractions. And this would be my final answer. Amy, are you good with that?
Yep, thank you.
You're welcome. So again, the key was just multiplying by the conjugate, and after that it's a relatively straightforward process. We just FOIL some stuff out and it becomes very much like a multiplication problem. It's just that first step that's the tricky one, but you can do it that same way every single time. Maria, you wanted to see 17. So let's go find 17. Okay. So this asks us to just solve using the method of our choice. So this is an equation that's written in standard form. So I have a couple of different options for something in standard form. I could try to factor it. I could use the quadratic formula. Or if I look at this, I could also think of this as a vertex form, since there's only x squareds and there's no extra x's. If I think about it in that way, I could use the reverse order of operations. So any of those 3 options would be appropriate here. You might try to factor it, but it's unfortunately not factorable. It looks like it might be that difference of 2 squares factoring, but because it's a plus and not a minus, it's not factorable. So that limits us either to doing a reverse order of operations or the quadratic formula. I would do the reverse order of operations in this case because I think it'll be the quickest, but it would not be wrong to use the quadratic formula here either. So using the reverse order of operations, I'll start by subtracting 25 from both sides. And then I'll divide both sides by 4. And then when we square root both sides, the squared cancels with the square root. Because I'm doing it to both sides, I get a plus or minus. And then I get a square root of a fraction as the square root of the numerator over the square root of the denominator. There's a couple of things that can happen here. Since I have the square root of a negative, I can take that take the thing or the negative sign out and put an I outside of the radical like this. And then I can just do those two square roots, right? The square root of 25 is just 5, and the square root of 4 is 2. So I'm left with plus or minus 5 over 2i. Now, you could have certainly used the quadratic formula here, and you would have ended up with the same spot. I think the simplification would have been probably a little messier, but still totally doable. But in a case like this, if I can use the reverse order of operations, I like to do that because it's usually very easy and fast. Okay, I think we had one more question here, number 10. Back. Okay. So number 10 was asking the absolute value of a complex number. To do the absolute value of a complex number, we just are going to do the square root of a squared. So 12 squared is 144, 18 squared I think is like 196 or something. No, that's not right. Whatever. Anyways, but the sum of these two is 468. And I recognize that 468 I could think of as 4 times 117. So this could really be the square root of 468 is the square root of 4 times the square root of 117. Well, 117 might be able to do a little bit better than that, huh? Yeah. Anyway, let's wait. 117 I can do better than. And 117 I recognize as 9 times 13. The square root of these three. So 2 times 3 times 13, or 6 root 13. The trickiest part there is just kind of like dealing with simplifying from here to here. Now, I wouldn't be terribly picky on a test if you didn't do that simplification, although if you did attempt to do it, I would expect that you do it correctly. But we'll talk later in a later chapter about really how to do that simplification a little bit more completely. So I don't expect you to have, like mastery of that right now. So in that kind of a problem, if you stopped at the square root of 468, that would be fine. Just keep in mind, if you were taking like a standardized test or something, that's not how they would write the answer. They would write the answer as 6 square root 13. And that's kind of how you get there, but I wouldn't expect that you're doing that right now. Eventually, yes, but for this section, or this chapter, no. Eric, are you happy there?
Yes, thank you.
Yeah, absolutely. Okay, 18 is up next. Okay. So for 18, this is a quadratic that's in standard form. So to do this, I would either need to try to factor it or use the quadratic formula. Since the leading coefficient is 1, I think trying to factor it to start would be an obvious place, since if that works, it's going to be very fast. But pretty quickly, we should see that it's not going to be factorable because there's not two numbers that multiply to give us 25 and also add to give us 12. So we're going to be stuck using the quadratic formula as our only option. So negative b plus or minus b squared minus 4 times a all over 2 times a. So 12 squared is 144, minus 100 is 44. And 44 I recognize as 4 times 11. So the square root of 44 can be the square root of 4 times the square root of 11. So I could rewrite that as 2 root 11 over 2. And then I could reduce it a little bit more by writing it as two separate fractions, because 12 over 2 is 6, or negative 12 over 2 becomes negative 6. And then 2 root 11 over 2 just cancels down to root 11. So this would be our best answer. Although again, like if you left it here, that wouldn't be wrong at this point. But keep in mind that if you're looking at a standardized test or something, that's not the way they would format their answer. Although if you typed both of those into your calculator, they would both give you the same decimal for the result. Natalia, are you happy with that?
Yeah, thank you.
You're welcome. Edmund, I'm gonna come back to yours because I'm gonna do this other homework 6 problem, and then we'll catch up with yours here after. So these will be the last 2 that we do. And Edmund, this is very much the same situation as 18. So again, you might try to factor this, but we'll see quite quickly that it's not factorable. So we're stuck using the quadratic formula. Or not stuck, but I should say limited to. So 8 squared is 64. 4 times 6 is 24. So 64 minus 24 is 40. And 40 we should see as 4 times 10. So that's the same as root 4 over or times root 10. Or just 2 root 10. And if we write this as separate fractions, we get a very similar situation as before. I get negative 4 plus or minus root 10. And again, like if you had stopped here, I would mark that wrong, you know. Okay. Oh, I'm sorry, Edmund. I was talking to. This was Amy's question that I was doing, but you guys caught what I was going on. All right. Let's grab homework 5. It's just the 1 page. Okay. And then we wanted to look at number 9. Oh, well, this is just me being dumb and not writing equals 0 on it. So they can't really solve it if it's not equal to something. So that's the first confusing part about number 9. Hopefully you just made the assumption that, like, I guess that probably was supposed to equal 0. In which case, again, now this could be a standard form polynomial or quadratic, so we could solve this either by factoring or using the quadratic formula. I can tell this one is factorable because there are 2 numbers that multiply to give me negative 30, 15 times negative 2, and add to give me 1. That would be positive 6 and negative 5. But I would still have to do like all that factor by grouping stuff to get there. The other option is to just plow ahead with the quadratic formula. Both of them are appropriate. Me personally, I would use the quadratic formula really anytime I see the leading coefficient isn't 1, because I don't think it's any more work to use the quadratic formula than it is to do like the full factoring method. If the leading coefficient is 1, I would check to see if I could factor it first before I tried to do the quadratic formula, because if I can use one of those shortcuts that is pretty much, you know, as fast as it can get. All right, so let's see. I have 1 and then 1 plus 120, so that's the square root of 121, which is just 11. And then I would break this into 2 chunks because of the plus or minus. So that gives me 10 over 30, or 1/3. And if it was subtraction, That would give me negative 12 over 30, or negative 2/5. And those would be my two answers there. Again, you could have factored that, but I don't think it would have been any faster than this. You should have gotten the same results if you did choose to factor. Okay? All right. So to this point, we have talked about simplifying and solving, and we're finished with those two topics. So we're going to start our third topic today, which is going to be graphing. Reminder, in each of these chapters, typically we worry about 4 skills: simplifying, solving, graphing, and modeling. For this chapter, the graphing and modeling chunks are going to be pretty quick in comparison. Most of the work was the simplifying and solving steps. So these last two topics will go quite quickly, probably a day or two at most for each of them. So we'll be probably wrapping up this chapter the week we come back from Thanksgiving, would be my supposition. Anyways, just to give you a heads up as to kind of how close to the end we are. So we'll start with a definition. So the graph of a quadratic is called a parabola. And for a quadratic function, those parabolas are either going to open up and be kind of U-shaped, or open down, still U-shaped. And if we are extending our option to deal with things that aren't necessarily functions, you could have quadratics that open left or open right. In those situations, so you'd have like y squareds and just x's. And those things aren't functions, so they're kind of beyond the scope of this class, but I wanted to mention that like parabolas could open left and right also. Basically, it's the same idea. You just, all your x's are like your y's, so you'd have like y squared plus 5y plus 7 is equal to x. And that's an example of a quadratic that would open to the right. But that's beyond the scope of what we're doing here. And it's easy to identify these quadratics about whether they're going to open up or open down, because it's all just based on the sign of that a value. When I say a, I'm talking about the leading coefficient for a standard form quadratic, or that factor outside of the parentheses in a vertex form, or that leading factor in intercept form. So when we say a, it doesn't matter what form we're talking about the same a in any of those. So if the a is positive, the parabola opens up, and if the a is negative, the parabola opens down. Hopefully that's kind of what you'd expect. It's very common-sensey that the positive one opens up and the negative one goes down, because that's how the numbers go on the y-axis, right? The positive stuff is up and the negative stuff is down. There are some key features for a parabola that we're going to be especially interested in. So let's say we have a parabola that looks like this. There's 4 key features that we're going to be interested in. The first one is called the vertex. So the vertex is just the highest or lowest point on the parabola. So if our parabola opens up, the vertex we're talking about is the lowest point, like the bottom of the U. And if our parabola opens down, vertex is the highest point, like the top of the hill. The next thing is the axis of symmetry. So all these parabolas are symmetric. By that we mean we can draw a line where if we look at that line, the one half of the graph is like a mirror image of the other half. So that axis of symmetry is this imaginary vertical line that goes right through the vertex, and it just divides the graph into two mirror images. The next thing is X-Intercepts. So in this case, the graph had two X-Intercepts, but that doesn't always have to be the case. A graph could have, or a parabola could have one X-intercept or no X-intercepts. So in the case where it had no X-intercepts, imagine the vertex is above the x-axis and the graph opens up, in which case the graph is already above the x-axis, and if it's just going upward, it can't ever intersect the x-axis, right? So we don't always have x-intercepts. And the last one is the y-intercept. And we always have a y-intercept. You notice that I didn't give like formal definitions for any of these points because these aren't something that I would expect you to ever, to give me a definition for. It's just kind of, if you can look at a graph and pick them out, that's as much as I would need you to do with this. So the vocab is just, if you're able to see where the things are, that's all you really need. So if we had a picture of the graph, it would be easy enough to find the coordinates for these things. You could just find the point and then read it off the graph. But what if you didn't want to go through all the hassle of actually drawing the graph? What if you just wanted to go straight from the equation to the key features? So we'll talk about how to do that here next. And I'm going to start at the bottom of the list and go up. So we're going to start with the y-intercept and then do the x-intercept, etc. So to do this, it's quite easy to find. All we need to do is plug 0 in for the x in our function and simplify. So let's do a couple of examples. So this example, we recognize a standard form. So to find the y-intercept, all I'm going to do is plug 0 in for the x's and simplify. So 0 squared is 0, 2 times 0 is 0, plus 5 times 0, which is 0, 0 plus 0 is 0, and 0 minus 8 is negative 8. So the y-intercept is the point 0 because we plug 0 in for x, comma negative 8 because the y is negative 8. If we have a vertex form, nothing really changes. We just start by plugging 0 in for x, and 0 plus 7 is 7, and 7 squared is 49, minus 20 is 29. So my y-intercept is 0, 29. Or if we had an intercept form, again, nothing is going to change. Just plugging 0. So 3 plus 0 is 0, or is 3. 0 minus 4 is negative 4. 2 times 3 times negative 4 is negative 24. So there's the point 0, negative 24. So that should be all pretty easy and familiar feeling, right? The same way you found y-intercepts for linear functions or linear equations, where you just plug 0 in for x. Next up are the x-intercepts. So to find the x-intercepts, you're going to plug the 0 in for y, and then solve for x. So let's do a couple of examples. Oops. So I recognize this is standard form. So when I plug 0 in for x, I have a standard form equation to solve. I can solve a standard form equation by using factoring or the quadratic formula. In this case, since the leading coefficient is 1, I'm going to try to factor it, because if it is factorable, it should be really easy to do. So I'm looking for the two numbers that multiply to give me 6 and add to give me 5. Those are 2 and 3. So I can then apply the zero product property. 0. And when I solve, I get x equals negative 2 and x equals negative 3, which gives me the points negative 2, 0 and negative 3, 0. And again, I'm getting a 0 in the y-coordinate place because we plug 0 in for y. And then the x values in my points are what I solved. Oops. So if I have a vertex form, not much changes. I still start by plugging 0 in for y. And then to solve a vertex form, what I'm going to need to do is I'm going to use the reverse order of operations. So I'll start by subtracting 8 from both sides, and then dividing both sides by negative 2. And then we'll square root both sides. The square root of 4 is 2, and I get the plus or minus because I did the square root to both sides. And then I subtract 3 from both sides. And this creates two answers. I get negative 3 plus 2, and I get negative 3 minus 2. So negative 1 and negative 5 are my values for x. So my 2 points are negative 1, 0 and negative 5, 0. One more example. Let's suppose we have an intercept form equation this time. Well, nothing changes on how I start. Plug 0 in for y. And now if I have an intercept form equation that's equal to 0, I can just apply the zero product property straight away. This is like the easiest possible situation. So 0 equals 5 is a bunch of nonsense. That part doesn't give me anything. But the other two parts I can solve. So I get -2, 0, and 10, 0 as my x-intercepts. So basically this just turns into a solving problem, just like the things that we've been working on. Nothing really has changed, right? It's still just a solving problem. Oops. Next up is the axis of symmetry. And to find the axis of symmetry, we're going to use some formulas, and we're going to have a different formula for each different form that our quadratic could be in. So if we're in standard form, our formula is x equals -b over 2a. Remember that the axis of symmetry is a vertical line, so it'll always, the equation for that vertical line will always be in the form of x equals. In vertex form, our axis of symmetry is just x equals h. And for intercept form, our formula is p plus q divided by 2. So these are important formulas. You'll need these so you'll want to make sure that you kind of highlight them in a note in your notes in a way that'll be easy to come back and find. So I put a little red box around mine so it'd be easy to come back and find them. So let's do some examples. So again, first thing I do is I recognize it's a standard form. Since it's standard form, I know I'm going to use the equation -b over 2a. So I have negative of 8 over 2 times 2. So I just get x equals -4. And again, that's the equation of a line, remember, so it doesn't become an ordered pair or anything, it just stays x equals -4. The equation for a vertical line. So the next example, we recognize that this is vertex form. So we'll use the equation x equals h. Remember that the h is this value, or is the opposite of whatever that value is. So just x equals -7. And we're done. That was lovely. Okay, one more example. We recognize just on sight that this is an intercept form. So the formula I need is x equals p plus q over 2. My value for p is the opposite of the first parenthesis, and my value for q is the opposite of the second parenthesis. So I have -3 plus 7 over 2. So that's 4 over 2, or just 2. So that's pretty easy, right? It just requires the formula to do, and the formulas are quite simple, right? It's easy to get the values for the formulas, and the formulas are all quite easy to compute. So that's not so bad. The last one is the vertex. So the vertex is an ordered pair. I'm going to refer to the x-coordinate as Vx, and the y-coordinate is Vy, just V for vertex, and then a subscript for whether I'm talking about the x or the y-coordinate. So the x-coordinate is the same as the axis of symmetry, which makes sense because we said that the axis of symmetry always goes through the vertex. So the vertex needs to have that same x-coordinate. So to find the y-coordinate for the vertex, we're just going to plug in the x-coordinate that we got from the axis of symmetry and just simplify down. So in examples I give, the first thing I would need to do is compute the axis of symmetry, right? Because that's going to give me the x-coordinate. Rather than coming up with 3 new examples and repeating the same calculations to get the axis of symmetry, I'm just going to use the 3 examples from the axis of symmetry problem and kind of continue on. Just in the interest of writing less and getting done earlier. So I'm just going to go back to those. So my Vx is just -4. And to get the y-coordinate, then I'm going to plug -4 in. So -4 squared is 16, and 2 times 16 is 32. -4 times 8 is -32. And then if I subtract 5 from that, I get -5. The next one, my x-coordinate is -7. My y-coordinate then is going to be just plugging -7. So -7 plus 7 is 0. 0 squared is 0. 0 times -2 is 0. So I'm left with just -11. And it's worth noting here, -11 was also the k. And for vertex form situations, you can find the vertex just on site. It's always going to be h comma k. Now you could do what we did there. It's not incorrect to do that, but that's a nice little shortcut that you can shortcut through having to plug the Vx back in. You can just pull Vy just from the k value. And then our last example, Vx is 2. Vy is going to be negative, and then 2 plus 3, and then 2 minus 7. So 2 plus 3 is 5. 2 minus 7 is -5. The negative of 5 times -5 is positive 25. So we have 2 as our vertex. again, not terribly difficult, right? Basically, you just use the formulas from the axis of symmetry, and then you plug in those results to get your other coordinate. So far, this should feel pretty okay, right? Nothing too terribly complicated. You have some formulas to remember, but that's not so bad. So if we want to draw the graph of a quadratic, we need the vertex. And then we're going to need 2 points on each side of the vertex. So let's just do a little example here. I guess that's fine. So let's say we're going to graph y equals 3x squared plus 12x minus 1. So to find the x-coordinate for the vertex, since this is in standard form, I'm going to do negative b over 2a. So it's going to be negative 12 over 2 times 3, which just comes out to be negative 2. To find the y-coordinate for the vertex, then, I'm going to plug that in. So negative 2 squared is 4. 3 times 4 is 12. 12 times negative 2 is negative 24. 12 minus 24 is negative 12. And then minus 1 more is negative 3. So there's my vertex, negative 2, negative 13. Now I'm going to make an XY table. So I need 5 total points. I need the vertex, and then 2 points on either side of the vertex. Now, any 2 points on either side of the vertex will be fine. So there's no reason to make anything to be sneaky about this. If I want points to the left of the vertex, I'm just going to pick some x values that are less than the x-coordinate on the vertex. If I want points right of the vertex, I'm just going to pick some x values that are bigger than the x-coordinate on the vertex. Any x's that are bigger or smaller than that vertex's x-coordinate are fine, but don't make your life harder than it needs to be. Pick numbers that are convenient to work with. I just picked the next whole numbers in a row. Okay. So now to find their corresponding y-coordinates, all I'm going to do is plug them back into the function. So we'll start with negative 4. So negative 4 squared is 16. 3 times 16 is 48. 12 times negative 4 is negative 48. 48 minus 48 is 0, and 0 minus 1 is just negative 1. Now let's plug the negative 3 in. Negative 3 squared is 9. 3 times 9 is 27. 12 times negative 3 is 36. 27 minus 36 is negative 9. Minus 1 is negative 10. And we continue going on. Plugging negative 1 in this time, we get negative 10. And when we plug 0 in this time, we get negative 1. So you might have noticed here that if we look at the y-coordinates in our xy table here, it seems that there's a pattern going on. And you might be thinking to yourself, does this pattern always hold? And the answer to that would be it can always hold depending on how you've chosen your x's. So the key here is that the distance from the vertex to these first points, either to left or right of the vertex, is the same, right? -3 is 1 unit from -2, and -2 is 1 unit from -1. Since the distance from the vertex for those 2 points is the same, their y-coordinate is going to be the same. That's why we have that mirroring symmetry going on. And similarly here, the distance between the first point and last point in the vertex is the same. So again, their y-coordinates are going to be the same. Now you might be thinking, well, Mr. Kulik, is there ever a time where, like, if I just kind of pick 4 numbers right in a row like that, that this wouldn't be the case? Sure. But it probably means that the x-coordinate of the vertex is a fraction. So imagine instead of -2, the x-coordinate of the vertex was like 2/3. Now, if you wanted to graph or wanted to pick x points that were all the same distance from that x-coordinate of the vertex, you'd end up having to get fractions again, which is fine, but that's a pain in the butt to plug those in to evaluate. Rather, I would probably just pick like -1, 0, have my 2/3, and then 1 and 2. Now, those are all different distances, so I'd have to plug all those numbers in to get their y-coordinates. But I'd rather plug in 4 whole numbers than plug in 2 fractions to evaluate. In addition, graphing the whole numbers is much easier on a sheet of paper than graphing a fraction, right? That requires a little bit of estimation that would rather not have to do. All right, anyways. So we'll plot our points now. These negative numbers are getting kind of rather small, so I'm going to go by 2s instead of 1s because I don't want to make 13 tick marks here. So 2, 4, 6, 8, 10, 12, 14. Let's see, so I have -4, -1. And then I have -3, -10. I have -2, -13. And I have -1, -10. And then I have 0, -1. So there's my graph. Again, when you're drawing your graph, make sure you draw it curved. Parabolas are curved, they're not straight lines, so don't draw it like it's a V. Try to make sure that you've drawn it so it's U-shaped. And then I'm not going to do another example where it's in standard form, or where it's if I have something in vertex form or intercept form, because it's really the same thing. It's not any different. Everything proceeds the same way. The only difference is like use a slightly different formula when finding the x-coordinate of the vertex, but otherwise it's the exact same idea. Which leaves one final graphing topic to talk about, domain and range. The domain is lovely because the domain for all quadratics is the same. It's -infinity to positive infinity, which is awesome, right? We love it when that happens, when the domain is always one thing. That makes it very easy to make sure we get that right. The range, though, is not always one thing, but it's always one of 2 things. So if the parabola opens up, that is that that leading coefficient is positive, the a value is positive, we go from the y-coordinate of the vertex up to positive infinity. Notice that the y-coordinate of the vertex has a bracket on it as opposed to a parenthesis. And then if the parabola opens down, we'll go from negative infinity up to the y-coordinate on the vertex. So if we go back to that previous problem we were just working on, we can write the domain and range for that. So the domain is easy. Obviously, that's just negative infinity to positive infinity. And the range, well, since the leading coefficient is 3, I know we're going to go from the y-coordinate of the vertex, which is negative 13, up to positive infinity. And that's all there is to it. Are there any questions about what we've done today so far? Good. This is where I want to end today. So I'm going to leave you with 2 assignments. So homework 7 is just another solving assignment. So I have just a variety of problems that I'm asking you to solve. Keeping in mind here, now that we have that quadratic program, the directions here say you must show your work. So you can certainly use your calculator program to check things, and I fully encourage you to do that. But you need to show some work as to how you're getting your answer. So even if you're using your calculator program, you should at least fill in the numbers to the quadratic formula before you write your answer. And then homework 8, I have 5 problems where I ask you to determine whether the parabola opens up or down, just looking at the a value. Write down the axis of symmetry using your formulas, and then find the vertex of the quadratic, which we talked about how to do also. I don't need you to graph these first 5, you're just doing those 3 things. So that should be pretty easy and pretty fast. And then the last 3 problems on homework 8, we are asking you to graph. In addition to drawing the graph, though, you need to make sure you provide a 5-point XY table with the vertex in the middle and 2 points on either side of the vertex. Okay, so this assignment should be relatively easy. I don't think any of those graphing techniques were too terribly complicated. I think that you should have a pretty easy time with those. At this point, I've done everything that I needed to do for today, so I'm gonna dismiss you guys here in a minute. In general, I'm gonna try to make sure on these days where we're doing virtual not to have 80 minutes of me talking to you on the computer. I think that's awful hard to sit through. My goal is under 60 minutes, which I think with the 10 minutes at the beginning where I talked about kind of how the course was going to start or how it was going to go on virtual, and the 5 minutes of me waiting to make sure everybody got here, and then I think that we were probably right around 60 minutes of me doing math. So that's kind of where I want to keep my cap at. So yeah, the last thing to do before you guys sign off of the Zoom call is to just type bye into the chat. Once you've done that, you're free to leave and work on your homework or have your lunch or get some exercise or some fresh air or stretch or whatever you need to do for the rest of your day. I'll see you guys on Monday. Nope, not Monday. Sometime after Thanksgiving. Have a good Thanksgiving.
Bye. Thank you.
You're welcome.
Thank you. Thank you.
You're welcome. Bye, Loretta.